Let's look at some applications of the dot product. One of the applications we saw in 2 dimensions, and it's true in any dimensions, is the angle between 2 vectors. And that's just a rearrangement of our dot product formula. No, it's the angle we want to find. We make cos theta the subject, and we get that u dot v over the magnitude of u times the magnitude of v. So if I wanted to find the angle between these 2 particular vectors, okay, dot product on the top, so 1 times -4, 2 times 2, 3 times 1, and then on the bottom the magnitude of each of those, I get 3 on 7 root 6, plug it into the calculator, and to the nearest degree I get 80 degrees. Another useful thing was this idea of vector projection, and there is our little formula we came up with. So if I want to project the vector u onto the vector v, then it's u dot v over v dot v times v. But make sure you read the question. In this particular one, it's not saying find the projection, but just the length of the projection. So when it's the length of the projection, it's still u dot v on the top, but on the bottom we get the magnitude of v, not the magnitude of v squared, which is very easy to make that mistake because in our projection formula we have v dot v, which is of course magnitude of v squared. But if it's just the length we want to find, then it's just magnitude of v, not magnitude of v squared. So we sub into that one and we get 5 on 3. So alright, let's do an actual one where we find in the projection itself. So u dot v on v dot v times v, 2 plus 3 minus 8 on the top, and then on the bottom 1 squared plus 1 squared plus 2 squared, but multiplied by that vector we're projecting onto. It's 3/4 of it. I could have left it factorized like this or expanded out like it doesn't really matter. I mean, either way describes that particular vector. Well, what about finding the perpendicular distance of a point from a line? Now, we've got a formula in 2 dimensions. Fantastic. In 3 dimensions, well, that formula then became point to a plane rather than point to a line, so how would we do it? And we can do it via vector projections. If I wanted to find the perpendicular distance of the point to the line, well then essentially if I draw up this right angle triangle, it's like I'm saying I'm going to project the point P onto that vector. It's the side PQ that I want to find the distance of. Now I know MQ is that projection, so that projection of P onto N. MQ, I could rewrite it another way because I could have gone, MP plus PQ. And if I rearrange that and make PQ the subject, now it's the magnitude of PQ that I want. So essentially, the distance we're looking for is the projection of P onto N minus P, but the magnitude of all that. So if I have to find the perpendicular distance from 102 to the line that joins 221 and 311, BA, I need to work out that particular vector. Head minus tail becomes -1 minus 2j plus k. I'm going to need to know BC as well, because that's what I'm projecting onto. That is I minus j. So the projection of what I've called P onto U minus P. So 1/2 of I minus j, that ends up being the projection when we put it into our formula. And minus I minus 2j plus k. I want the magnitude of that. And that turns out to be the square root of 22 on 2. Classify the triangle formed by joining these 3 points. The sides are going to be the different vectors, so let's work those out. So AB would be 3, 2, 1, head minus tail. BC ends up being -2, -2, -2, and CA equals -1, 0, and 1. To classify the triangle, well, we normally classify them by their sides, isosceles, scalene, equilateral, that sort of thing, or angles, right angle triangle, acute angle triangle. I'm going to look at the sides, length of the sides, see if I can pick anything there. So the magnitude of AB turns out to be root 14, BC root 12, and CA root 2. Now I notice with those 3 we satisfy Pythagoras' theorem, because the CA squared plus the BC squared would equal the AB squared. So I've got a right angle triangle. Now knowing the answer, the other way I could have therefore done it is I could have looked at the vectors BC and CA and noticed, oh hang on, their dot product's going to be 0. Therefore I've got a right angled triangle because BC must be perpendicular to CA. That's another way I could have done that one. ABCD is the base of a square pyramid, side 2 units. V is our vertex. The pyramid is symmetrical. So basically that's telling me the vertex is right above the centre of the base. Calculate the acute angle between one of the slant edges and the base of the pyramid. So this is like these 3-dimensional trig problems that we did last year, but now we're going to use vectors to solve the problem. So what I'm going to do, I'm going to sit the pyramid so that it's sitting on the XY plane. And it makes sense to put the vertex on the Z axis because it would be nice and symmetric. Now if that's the case, I can work out some points here, and that means I can work out the vectors. The slant edge, that's one of the things they've talked about. So I'll use the one that's closest to me here, and that would have coordinates there of 1, 1, 0, because I've sat it so it's symmetric. They told me the length of the sides was 2, so there must be 1 either side of the axis. And the height is 4, so the vertex there must be at 0, 0, 4. Well, that tells me that vector is -1, -1, 4. But I've got to find the angle between that and the base. So the other vector I would like would be the one that joins this 1, 1, 0 to the origin, because then that'll create a triangle there, and we can find the angle in between those two vectors. And that vector then is -1, -1, 0, because noticing where I've placed the head's at the origin there. Now I've done that because whenever we're working out the angle between two vectors, we do it at the tail. Okay, let's work out the angle between them. So using cos theta is u dot v on magnitude u, magnitude v. Subbing in, cos theta is 1/3, 71 degrees to the nearest degree. Medians of a triangle meet at a point. Prove that they divide each other in the ratio 2 to 1. Well, I'll just draw up a triangle. I'll make this O, so I'm thinking of it as the origin, because I'm going to use vectors, and I'll just call the other two A, B. That means OA, I'll just be the vector A. There's my position vector. And OB will be B. X, I'll call the midpoint, because remember a median is a line that joins the midpoint on one side to the vertex, the opposite vertex. So I'll need that. I'll call that one X, and I'll call that one Y, and I'll just draw those two medians in, and I'll say they'll meet at Z. I'm also then going to join O to Z. Let Z divide AY in the ratio M to N. The vector AZ over the vector ZY would be in the ratio M to N. Playing around with all that, and the vector being head minus tail, I come up with this little expression here that M plus N times the vector Z would be NA plus MB on 2. But look, I could have chose either median, it didn't really matter. We just want to find the ratio, and the ratio is going to be the same on both, because I'm doing the same thing. I'm just getting a median and cutting it with a median. So Z would also cut BX in that same ratio. Well, that therefore means I could have got M plus NZ equals NB plus MA on 2, because all I really did between it is I've swapped the medians, so the A and the B basically have swapped round in those calculations. Well, therefore, if they're both M plus N times Z, they've got to be the same thing. Remember, we're trying to work out what is this ratio M to N. So rearrange it and group the M's on one side and the N's on the other. Nicely, we've got this common factor of the vector B minus the vector A, which can cancel out. And we get our ratio. M to N is 2 to 1. So yeah, they do. They divide each other in the ratio 2 to 1. So playing with vectors and the dot product.